Understanding physics. This is a paper 3 workout, the kind of practical paper. Nearly all of it applies to AQA and OCR. Okay, so let's dive in. Let's have a workout. Yes. Right then, using an oscilloscope, you know how to do that. This is a trace. It's called a trace. And it's basically a picture of a signal. It's voltage against time for a signal. There's two knobs on the oscilloscope that we're interested in. Volts per division, and that's vertically. So vertically, volts per division. So if it's set to 10 millivolts per division, then what's the amplitude of this signal? Work it out yourself. Answer coming soon. The other button that we're interested in is called the time base, or it's just time per division, and that is horizontally. So each square, as I said, it's like a graph of voltage against time. So each of these big squares represents a certain amount of time. For example, if it's set to 5 milliseconds per division, then what is the period? Yes, the time for one oscillation. What's the period and therefore the frequency of this signal? Work that out for yourself, and the answers are, there you go. So 26 millivolts, because from the middle, 10, 20, and I reckon that's about a sixth of, no, like 60% of the way up, if you like. So 26 millivolts. You can actually change the volts per division. You want it so that it kind of, the trace fills most of the screen. Yes. On the time base, what you would do is, now the period I said was 10 milliseconds. So from there to there is 2 divisions. There is actually a knob on the oscilloscope so that you can move the trace that way so that it actually starts on a line. And also what you would do is you would count the number of divisions for as many cycles as possible. So 1, 2, 3, 4, yes, is, and then count it for 4 and then divide by 4. So I get 2 squares for each cycle, and so that's 10 milliseconds. So the frequency is 100 hertz. Reading a scale might be very, very, very straightforward. Like this one here is just going to be 3.8 kilograms down the bottom there. Remember a meniscus? I've seen a couple of questions where you read to the bottom of the meniscus, so that's going to be 6.2, isn't it? Yes, because each scale division is 0.2. With voltmeters and ammeters, look at what the, it's called the FSD, the full scale division, yeah, or full scale deflection rather. Looking at this, we are on 0 to 5 amps, so we are on the top scale, aren't we? 0 to 5. So this reading here is going to be about 2 amps. If we were plugged into there, then the full scale deflection would be 1 amp and the reading would be 0.4. There you go, 2 amps. Reading a vernier. Now this is something that only AQA have to do. OCR don't have to worry about this. And what we do is look at this 0 here, and for the number of millimeters, this is measuring distance in millimeters. So the number of millimeters, 35, 36, 37. So it's 37, there's 37 millimeters there. 37 plus like some fraction of a millimeter. What is that fraction of a millimeter? You look where 2 lines line up. Now 2 lines line up here, don't they, on both scales? Yes, if you look before it and look after it, and they line up on the 7 on the top scale, so that is 37.7 millimeters. No, it isn't. It's 37.8 millimeters. Beg your pardon, isn't it? 5, 6, 7, 8. Yeah. Another tip: don't make stupid mistakes like that. 37.8 millimeters. There you go. Uncertainty. Yes. Now, there is always uncertainty. Yes, there's absolute uncertainty. It's 50 plus or minus 2 millimeters. There's fractional, which is very, very rare actually. I can't say I've actually seen a question where it asks about fractional uncertainty, but it does mention it in the syllabus. Percentage uncertainty, very important. So 2 divided by 50 times 100, 4%. So absolute uncertainty is what the uncertainty actually is. Percentage uncertainty, very important. How do you estimate uncertainty? And an important point is that you always estimate it. You can't, well, because you're uncertain about it, you know, by definition. If you use that ruler there, what would be the uncertainty? Well, the smallest scale division is 1 millimeter. So the resolution of that ruler is 1 millimeter. So I would say that the uncertainty is plus or minus half a millimeter. Yes? So you can estimate the uncertainty from the resolution of the measuring instrument. Also from a set of results. A student takes these repeat readings, estimate the uncertainty. So what's the uncertainty? Now, there's actually a couple of ways of doing it. One way of doing, oh, there's the first one. One way of doing it is it's half of the range. So from 2.2 to 2.6, the difference is 0.4, divide by 2, and that's 0.2. So half of the range. Another one is you work out the average, work out the mean, and then it's the biggest difference between the mean and either the highest or the lowest reading. And it should be about the same. If it's a normal distribution, it should be about the same. So the biggest difference to the average is about 0.22, and that gives a percentage uncertainty of 9.2%. You can get uncertainty from a graph. Very often there's lots of situations where we actually get the value of something from a graph, like Planck's constant or acceleration due to gravity, and a few more as well, internal resistance. So what you do is you do a line of best fit, and if you like, that's your average. Then you do a line of worst fit, and the rule is it should go through all of the error bars. Work out the value for the line of worst fit, and then the difference between them is the uncertainty in the gradient. Work out the value of whatever it is for both of them, and then you can work out the uncertainty from that, from the difference between them. A few more notes about uncertainty. If you measure something bigger, then the absolute uncertainty is the same. You know, if you measure something small, like let's say you're timing 5 seconds and then you're timing 100 seconds, the absolute uncertainty is the same, but the percentage uncertainty is smaller. So it's always a good idea to make whatever you're measuring bigger. For example, with a diffraction grating, if you just measure the angle to the first order, then that's a pretty small angle. What you could do, in fact what you should do, is measure the angle between, let's say here you've got 2/3 orders there. If you measure that angle between them and then divide by 2 and then work it out for the third order, and that will give you a better answer. Yeah, there will be less uncertainty. If it's plus or minus 1 degree, then the percentage uncertainty will be a lot smaller. If you're timing the period of a pendulum, I'll talk more about pendulums later, you do it for 10 oscillations and then divide by 10. In Young's double slit experiment, and these are what we call fringes, you measure the distance between 10 fringes and divide by 10. Yeah, measure something bigger and the percentage uncertainty is smaller. Combining uncertainties, this is very, very important. Okay, this will 100% come up. If your voltage is plus or minus 5%, if your current is plus or minus 3%, then the power, P equals VI, what will the uncertainty be? The resistance, R equals V divided by I, what will the uncertainty be? And you should know by now that it is, there you go. So for the power, 8%. If you multiply quantities together, you add the uncertainties together. If you square a quantity, like if you're working out the area, then the uncertainty in the radius, you would double. If you're working out the volume, then the uncertainty in the radius, you would treble. And if you are dividing R equals V over I, again, you add the uncertainties. Okay, because you might be using the biggest value of V and the smallest value of I. Yeah, so whether you're multiplying or dividing, you add the uncertainties. Right then, moving on. A student takes multiple readings of intensity at different distances. It might be light intensity, it might be gamma radiation with distance. He suggests that I follows an inverse square relationship with distance. In other words, he suggests that the intensity is proportional to 1 over x squared. And we've got some data here from his experiment. So do you agree that it follows that relationship? How would you test that relationship? So have a little think, you should know how to do this. And basically, if I equals a constant over x squared, then I times x squared equals a constant. Okay, so you work out the value of ix squared, and do you get the same number every time? Now, we're not going to get exactly the same number because, I mean, radioactive decay, for example, is a random process. Be very, very surprised if you got the same number every time. But within, let's say, 2 sig figs, it's pretty close. There isn't a trend of it getting bigger or smaller. I would say they are close enough to justify the relationship. So remember that to work out, to prove a relationship, change it to something equals a constant times or divided by something, then work out the value of the constant, and is it constant? This is a special one. How would you prove that a relationship was exponential? Now, if you had the whole graph, you know, like a radioactive decay graph of activity against time, then, you know, you could find the half-life, and what you should find is that the half-life is constant. Okay, and it doesn't have to be a half, then a half, then a half. You know, you could go from any value to half of that value. So constant half-life. From the numbers, one thing you would do, maybe if you had the time, which you probably won't in an exam, is if you plot the graph of the log, the natural log of the height against time, then you should get a straight line, and that shows that it's exponential. The way I would do it in an exam is, now, so plot log h against t, right, the height should fall by the same fraction in equal amounts of time. That time doesn't have to be the half-life, it can be any amount of time. In this case, just do it every 20 seconds. So the height should fall by the same fraction in equal amounts of time. So from 0 to 20, it goes down by 1.25. From 20 to 40, 1.26. From 40 to 60, 1.26, etc. So it's going down by the same fraction in equal amounts of time. Or in any amount of time, it goes down by the same fraction. You may be asked to actually plan an experiment. It'll probably be something the same as or very, very similar to one that you did in your PAGs, yeah, your practical assessments. Make sure you say what this is very GCSE, but make sure you say what the independent variable is, the thing that you're going to change. The dependent variable is the thing that you're going to measure because it depends on the independent variable. And then control variables, things that you keep the same so that they don't have an effect on the result. They don't change the pattern that you're looking for to make it a fair test. Okay. Few notes about radioactivity. Safety is all about minimizing exposure, because nuclear radiation is ionizing, and because it's ionizing, that makes it dangerous. It damages living tissue and can cause cancer as well. So you minimize exposure in terms of how close you are to it, in terms of how long you are exposed to it, in terms of protecting yourself from exposure. So you don't handle it directly. You always handle sources with tongs. You might want to wear gloves as well. Never point it towards anybody. If you're not using it, keep it in lead-lined containers when it's not in use. And if you haven't been properly trained to use it, then you shouldn't be using it. Okay. Correcting for background, you take a reading for at least a minute when there's no radioactive source there, and then you subtract that from all of the other readings. Okay. Remember to correct for background radiation. Pendulums, time for 10 oscillations and divide by 10. Time when the bob passes a fiducial marker. Now, a fiducial marker basically means that there's the bob and you have some kind of a marker on the table, and you time it when it goes past that marker. Yes, in that direction or whatever direction. And that's called a fiducial marker. And that's the correct way of timing a pendulum. Make sure your supports are rigid, so they're clamped to the bench, for example. Make sure you measure the length to the center of mass of the bob. And something I haven't written here is small amplitude oscillations. Just, a couple of centimeters. The pendulum just needs to be swinging like that. Okay, not like that. Why? Because in the derivation of t equals 2 pi root L over g, there's a small angle approximation. So for big amplitude oscillations, that's big angles, and the equation doesn't work. If you're getting a value for little g, then from t is 2 pi root L over g, square both sides, whatever, t squared against L, the gradient is 4 pi squared over g. Types of error. There are random errors. These are natural, unavoidable variations in your measurements. If you measure the same thing 10 times, you're not going to get exactly the same answer every time. So there is a natural, unavoidable variation. There'll be a normal distribution of readings. They affect the precision of a group of readings. If you're talking about a group of readings, precision is how close together they are. Okay, this is why we take repeat readings. This is why we take several readings, because then we average. We are reducing the effect. We are minimizing the effect of random errors. There's one type of random error called a blunder, which is just basically you wrote down the wrong number, or you made a stupid mistake, a blunder. Systematic errors, the same error affects every reading. Okay, so there will be, for example, if your reaction time, human reaction time, well, if you're timing something, then it will always be bigger. A problem with the method or a problem with the equipment, zero error. If the instrument, like a scale or a voltmeter or whatever, hasn't been properly calibrated and it doesn't read zero when it's supposed to, that's called a zero error. Parallax error, that comes up very often. Parallax error is basically if you're measuring something, let's say you've got a bouncing ball and you want to measure the height that it bounces at, then your eye should be at the level that it bounces at, and you've got, let's say there's a ruler over there. Okay, so your eye level should be there. If you're looking from above, then the reading will be smaller. If you're looking from below, then the reading will be bigger. So basically it depends on the viewing point of the observer. It's called parallax error. I think this might be the last slide. EMF and internal resistance from a graph. So you build this circuit, obviously ammeter in series, voltmeter in parallel, perfect ammeter has 0 resistance, perfect voltmeter has infinite resistance, and all you do is you change the resistance of this rheostat. You measure the terminal PD, the voltage across the cell, and you measure the current. You plot terminal PD against current. You get a straight line from y equals mx plus c. Yeah, y equals mx plus c. The gradient is the internal resistance minus little r, and the intercept is the EMF. Have I covered everything? No. The video would be ridiculously long. I've covered, if you like, I've guessed a few things which might come up on the exam. Some things will definitely come up, like combining uncertainties will definitely come up. Okay, so if you're year 13 and you're coming up to your exams, maybe you're coming up to paper 3, I just want to say thank you for supporting my channel. Hopefully you found my videos useful. Spread the word. My channel is growing steadily. There's quite a lot of competition, lots of other physics ones out there. Hopefully you've appreciated my style, very kind of nuts and bolts. This is what you need to know. Good luck in the exam and in your future. I hope you get the grades that you need and you go off and do wonderful things. Okay, so bye-bye.